Okay, let's start today's lecture with a recap of what we had done in the previous lecture. In the previous lecture, we had started talking about the one-dimensional finite element program. Here we had outlined what are the various building blocks of the finite element program, and we had said that it consists of the preprocessor, the processor and the post-processor. In the previous lecture, we had outlined how to make the mesh, how to read the input data and how to make the mesh, given the kind of features that we wanted to incorporate in a program. In this lecture, we will take that further. So, we will go beyond the mesh, we will try to see what are the other building blocks we need. Once all these building blocks are there, then we have essentially everything that we need to make our one-dimensional finite element program. Let us go and see the basic structure of the finite element program and the various pieces that we need. So, we have come to the one-dimensional finite element program that we need to develop. So, here as we had said, the preprocessor is what we were at. We had already done the part about reading the input data. We had created this routine called read input, and what we had done here is we had read in the geometric data, the loading data, the material data and the boundary data, and also what kind of meshing we needed, that is how many elements in each piece, what is the order of approximation and so on. So, these are all the data that were inputted in the read data program. So, next what we do is we had looked at how to make the mesh. This was, as we had given a name, done through a subprogram or a subroutine called make mesh. What was the idea is, given the mesh data and the material data and the loading data that is available to us, we would like to make the mesh in a particular way so that it honors the material transitions, the places where the points where point loads are applied, and if need be, we can have also different size meshes in different regions. So, that is what we had done. So, here the mesh was divided into the piecewise uniform meshes, okay, that is in each piece. If I have a piece here, this domain, in each piece I have a different size element, and these are the transitions coming due to the material and the point load. So, given the mesh, in the mesh what did we want to make? We made the set of nodes and their global coordinates given by x of I. Then we went and created the elements, and we said that for an element I would like to know what are the extremities, that is the two nodes at the two ends of the elements. So, this data was given in the nodes I comma j array. These arrays were created. At the same time, while we are making the mesh, because we know these transition points, material transition points, and also the point where the point load is applied, while we are making the mesh, at the same time we can extract out the name of the element at the end of which the point load is applied. So, if this is the element, here is the point load applied, okay. So, we will extract out the name of that element and we will call it IPT. It is not sacrosanct, but we can do it like this, okay. One can give any name that he wishes. I choose to give IPT. Now, once the mesh is ready, then what do we do? Here we had also obtained these parameters any LEM. Any LEM is the total number of elements that we have in the mesh. Also we had the total number of nodes in the mesh given by NNODE. Now what did we say? That using the order of approximation P, which is given to us, we had assumed uniform approximation and the linear variation of the material, the cross-sectional area given by Ax, quadratic variation of Fx, the maximum order of the integrand is obtained. This we had discussed in detail in an earlier lecture. Based on this, the value of n, that is the what point rule I have to use in the Gauss quadrature rule, this n is selected. Given this n, now we can get the integration points and the corresponding weights from the routine integ points. Okay. So these are the things that this routine will do for us, the integ points routine. Okay. After the integ point routine has been obtained, then we had also developed the routine shape as discussed in the previous lecture, where we could output the shape functions and their derivatives using the Lagrangian definitions for order P up to 4. So we can get up to the 4th order shape functions. Okay. So this routine shape would output that. Then we had decided to have another routine which will take these integration points that we have obtained out of integ points, and at these integration points it is going to output the value of the shape functions and their derivatives in the master element and store them away. This was done in the routine called shape-all. Why was this needed? This was needed for our element calculation, because as we are looping over the elements, trying to compute the element stiffness matrix and the load vectors, we do not want to call the shape function program at every integration point, get the output of the shape function, use it, and then go to the next one. This causes repetitive work, and that costs in terms of time. So what we said, over the integration points, since they are the same for each element, we will call the shape functions, store them away, and in the elements, as we go and do the element calculations, we are simply going to read out those values from this stored set. Okay. Then comes this program to number the global degrees of freedom. So what we have done is, till now we had discussed this point. Now what we want to do is, we would like to enumerate the degrees of freedom in the element. How are we going to enumerate the degrees of freedom? What do we mean by that? So let's say this is my mesh. I have a quadratic approximation. So how many global basis functions we have? We have 1, 2, 3, 4 and 5. So I have taken a 2-element mesh where I have these 5 global basis functions. Okay. Now how do I construct them? So what we do is, we have the subroutine or the function called DOF number, where we will go element by element, construct these global basis functions and give a one-to-one correspondence between these global basis functions and the element level degree of freedom. I.e., that is, if I am in element 2, for example, this was my N1, this was my N2 and this was my N3 for element 2. Now which global basis functions phi does this N1, N2, N3 correspond? This data we are going to construct in this routine. So if you see N1, the local, that is the element 2's 1 corresponds to global 3, 2 corresponds to 4 and 3 corresponds to 5. So how do we go about doing it? So we have the total number of degrees of freedom in the mesh given by NN DOFs, and we initialize it to 1. Then we start the loop over the elements. Okay. As we loop over the elements, then we have this array IL DOFs I comma 1. Okay. What is I? I is the element index, and this the second one, which is j, this is the local degree of freedom, that is whether it's 1, 2, 3. For every element, how many we'll have? We'll have p plus 1 such degrees of freedom in the element. So what am I going to do to the if you see, for element 1, here I said IL doffs I comma 1 is equal to NN doffs. What does it mean? So for element 1, the first degree of freedom of the element 1 corresponds to the global 1. Okay. Then I go over the remaining p degrees of freedom in the element, and I keep on constructing these global degrees of freedom and updating my element to the global connectivity. So you see that I am going over, looping over this j equal to 1 to p. I increment the NN doffs, that is the total number of degrees of freedom, remembering that I should not repeat this increment. So that is 1 degree of freedom should not be counted twice. So I increment this degree of freedom count. Then what do I do? For this element I set, now what happens, 1 is already set, so 2 becomes NN doffs, the new NN doffs, then 3 becomes the new NN doffs, and so on. I keep on doing this. If you see this for our 2 element mesh, what happens? For element 1, NN doffs 1 is 1 starting off, so I get for element 1 the first entry is the global 1, which is what we have here. For NN doffs, now I loop over p. So p, because I have taken 2, it will be 2. So then I increment my NN doffs, it becomes 2. Then for the element 1, the second one becomes 2. You see, second one becomes 2. Then I go and increment my NN doffs again, and this becomes 3. Then for the element 1, the third one becomes 3. Then I go to element 2. Now when I come to element 2, okay, what happens to the first one of element 2? It should be 3. Now my count here has stopped at 3, so the first one of element 2 automatically becomes 3. Then the second one of element 2, I come here in this loop, I add, it becomes 4, so it makes it 4, and the third one, it makes it 5. So you see that this way, for any p, we can keep on constructing these global degrees of freedom, okay, and assigning to the element this connectivity between the element 1, 2, 3 up to p plus 1 to the global ijk. Okay. So this I am going to do in a loop. So once I have done this, then I stop my loop over the element degrees of freedom, loop over the elements, and I have essentially the one-to-one correspondence between the local degrees of freedom in the element to the global degrees of freedom in the domain. So here I will have the local to global connectivity. This is very important from the point of view of adding up the element entries to get the global stiffness matrix and the load vector entries. So with this, once we have made we have read in the input data, we have made the mesh, we have obtained our integration points and stored as a additional part the values of the shape functions at these integration points, then constructed the enumeration of the degrees of freedom, then our preprocessor has ended. This job has to be done irrespective of what problem I am going to solve. What is the EA, what is the F, that is going to be used next. So the preprocessor ends here. Then we come to our processor. So we come to our processor. What does the processor really do? Processor is essentially the main building block where I am going to start constructing for the given problem, that is for the material data, loading data, boundary conditions. I am going to construct the global stiffness matrix K and the global load vector F, apply the boundary conditions, and then solve the problem. This is what our processor is going to do. So the first part of the processor is the assembly program. What should it do? It is going to essentially, we will call it by the name assemble. Again, we can call it any name. So first job is to initialize our global matrices. So I am calling my global stiffness matrix as SK glob. One can call it any name. And the global load vector F glob. So SK glob is essentially of size n doff by n doff, and F glob is of size n doff. You see what had happened in a previous program, as we kept on adding the degrees of freedom, our counter for the total number of degrees of freedom kept on getting incremented, and at the end of the program we had the total number of degrees of freedom in the domain. Okay. So once we have all this, we have the n doff and so on. So we can first initialize the global stiffness and the load vector. Then we say, okay, in the element, how many degrees of freedom are going to be active? And given the order of approximation p, it is going to be p plus 1. So we name another variable called n doff, which is equal to p plus 1. Then we start looping over the elements. This is the crucial part of the assemble program. Here, as we start looping over the elements, then for the element, as we had created this LMK routine, which was used to give us the element stiffness and the load vector entries, I will call this routine for each of the elements I, as I am looping over the elements, okay, giving the input data that is needed and getting the output data in the form that we need. So it gives out to me the element stiffness matrix SKEL and the element load vector FEL. Now SKEL is of size n doff by n doff, and the load vector is of size n doff. Okay. So it is of size p plus 1 by p plus 1, and this is what we get. Now where do we put it? In the global stiffness matrix and the load vector. That is what we need from the assembly point of view. Okay. So for that we start looping over the degrees of freedom for the element. That is, we loop over j equal to 1 to n doff. As we are looping over the degrees of freedom for the element, then for each of these degree of freedom I get its global name. Okay. So for the element I, somehow this has become big I, it should have been small I. For the element I take the local j, and from our what we had done in the previous routine, from there we now are able to find what is the global name of this degree of freedom. Okay. So it is, we call it by JGL, that is J global. Okay. Then what do? We have obtained the element level load vector. So we take the corresponding global load vector entry, that is given by JGL. So F global entry, that is the number here is, if I do this, so this is my JGL. So to this entry I now add the element entry. Okay. So there is a one-to-one correspondence between the J and the JGL, through which I add now this element entry in the global entry. Once I have done that, then I go over, so this is essentially a loop over the rows. Okay. So essentially I am looping over the global rows, to that I am adding the local rows in the right positions. This is for the load vector. Now similarly I will have to loop over the columns. Okay. So I will have the, so these are my rows and these are my columns. So I start looping over the columns and I call them by the variable k. Again I loop over the number of degrees of freedom which are there in the element. Again I find the global name of the element degree of freedom k. Okay. So for the element I find the global name KGL corresponding to k. Then once I have the global name of the column and the row in which corresponding to which my this element entry has been obtained, then I am going to simply add that entry in the corresponding global row and column, and that's what exactly I am doing here. So in the SK globe, that is the global stiffness matrix, I go to the global row, the global column, to that I add the local row and the local column entry, and I am done. Then essentially I end the loop over the columns, then I end the loop over the rows, and I end the loop over the integration points. You see, one thing that I have tried to do in this construction, though this is not the full-fledged program, is that I have done my writing in an indented way. That is, if I have a loop, the outer loop, which is the loop over the elements, then I will essentially, you see that these 2 points match. The end loop for the outer loop matches with the for where it starts. Now everything inside this outer loop is indented. So generally one indents by 3 or 4 empty spaces, and then I start this part, writing the inner part. In the inner part I come to this loop, another embedded loop. This loop ends here. Okay. See that this loop is over the rows. Now again whatever is inside this loop is again indented, okay, nicely indented, so that you can very clearly see the embedding of the loops inside each other, and that essentially is a very important thing from debugging point of view, from writing the program point of view. First of all, it looks very nice, and secondly, you will not be mixing up the loops. Okay, you see the third loop, the innermost loop is the loop over the columns, which ends first, then the outer loop, then the outermost loop over the elements ends. Okay, so this is something that a student should keep in mind when writing the program. Then for this we needed the element calculations which come in here. Those element calculations will be provided by our routine LMK, which we had already discussed in the 13th lecture. So now after we have assembled our global, the local, the element stiffness and the load vector entries into the global stiffness and the global load vector entries, then what are we left with? First we have to account for the point loads. So now to account for the point loads, I have a routine called point underscore load. One can give any name. Okay. For this routine, from the meshing routine, I have already extracted the name of the element at the second node of which, or the last node of which, the point load is applied. So I know the name of this element IPT. Okay. Now I know that for this element, how many degrees of freedom are there? There are p plus 1 degrees of freedom. So I go to the last degree of freedom, because if you remember in the element, this one is the p plus 1 degree of freedom, this is the first one, and you have the others in between. So I take the p plus 1 degree of freedom, I find its global name, again using my ILDOFs. You see how crucial this ILDOFs information becomes, and this is the kind of data structure that will also be used in the 2D and 3D programs, because their life will be a little bit more difficult. Okay. So I find the global name of this degree of freedom. Okay. Then things are very simple. Then I simply go to the corresponding entry in the global load vector, okay, and to which I add essentially the point load, the value of the point load. The value in this case we mean that it's the positive direction. So point load is acting in the positive direction. So if I have to have a negative point load, I should give it as a minus value. Okay. So it is going to add this value to the corresponding entry, as simple as that. Why is it going to add to that corresponding entry? Because the only V which is non-zero here is this IGB name, that is the basis function corresponding to this one. Okay. So once we have this, then we have taken care of the point load, and here we have decided to add only one point load. You see that an extension of this to take care of multiple point loads is also not difficult. We have to find essentially the locations of the point of application of these loads, find the corresponding elements at the extremity of which it is being applied, and then simply go and find the global degree of freedom corresponding to this extremity and add the value of the point load to that corresponding load vector entry. So this is how we will take care of point loads. Next we have to, so we have now taken care of point loads. What is left? We have not yet handled the boundary conditions. So now we have to apply the boundary conditions to our problem. Okay. So we have a routine called boundary. Okay. This routine essentially will do the job of applying the boundary conditions, and this part has to be done very, very carefully, because if this is wrong, my answers are going to be wrong. Okay. So how does the boundary condition routine function? So what we have in our domain, we have the two extremities. That's where the boundary conditions have to be applied. The first extremity is the point 1, is the degree of freedom 1. The next extremity is the degree of freedom in end of. Okay. So this is where the action has to be, at these two extremities. So we say that, okay, let this extremity corresponds to the point x0, that is the first point. Okay. Now we say that we go to this point x0, and here we would like to first apply the boundary condition that has been specified for the point x0. Okay. So as we had done in the input data, we had said, okay, tell me, I have asked the user, tell me what kind of boundary condition you want to specify at this end, and that is given by this flag IBC type 1. If it is equal to 1, then it is a Dirichlet type boundary condition, that is I am going to fix the value of the displacement at that point. If it is type 2, then it is a Neumann type of boundary condition, that is I am going to fix the value of the load at this point, that is I am applying a point load there. If it is of type 3, then it is a mixed or a Robin type of boundary condition, that is here if we have, that is I am going to have an end spring, okay, which applies a load which is a function of the end deflection itself. So this is what we meant by the mixed condition. So here how are we going to do these things, take care of these various types of boundary conditions that can be applied in this problem. Okay. So let us see first the Dirichlet type. So for the Dirichlet type, here I am going to specify the value of the deformation here, and this is given by u0, the displacement at this end, this is given by the value u0. u0 need not be 0 always. So I am giving you the value of u0, and I want to enforce this in our calculations in such a way that indeed the displacement at this point 1 comes out to be u0. So how do I do it? So to do it, what do I do is, in the global stiffness, I go and take the first diagonal term 1 comma 1 and I set it to a value of 1. Okay. So I have the global stiffness, I take the first diagonal term, set it to a value 1. Okay. Then correspondingly the first load term, I am going to set it, I had calculated something, but now I am going to overwrite it and set it to the given value of the displacement u0. Now what do I have to do? If you remember, u0 is already known, so it has to be eliminated from the rest of the equation. So what do? I loop over the rest of the columns in the first row, that is column 2 to column n end offs. Okay. I loop over these columns and I simply set the value of these column entries to 0. So that is, I am going to set this one to 1 and everything else I am going to set to 0. Okay. So what does it give? So my first equation gives this is equal to u0, so I get u1 is equal to u0 automatically. Okay. Now what do I have to do? Since in the remaining equations also u0 is sitting there, I have set this 0, I would like to now keep my stiffness matrix symmetric. I could have left it as such, but by leaving these entries here, these stiffness entries which are not equal to 0, I am destroying the symmetry of the stiffness matrix. So now to make the stiffness matrix symmetric, I simply eliminate this known degree of freedom from the remaining equations. So what do I do? So I go to the remaining rows. So the next row, I know the value of u1 is u0. So I simply remove this part from here. How? By first changing my f glob corresponding to that entry, that is from the second, third, fourth up to n and offs, to what it was originally minus the part due to this stiffness term multiplied by u0. This is what is known. Okay. So I subtract that, and now this is my modified load entry from 2 to n and offs. Then I go and set the entries in the first column for all the rows, remaining rows, to 0. So I have set it to 0, that is I have removed the influence of u1, and the influence has been carried over to the load vector side by writing fj is equal to fj minus kj comma 1 into u0. Okay. So this is how I am going to take care of the Dirichlet boundary condition applied at point 1, and this also retains the symmetry of the matrix that we have. Next is, if I want to have a Neumann boundary condition at this end, that is at this end I have a force Q applied. Q is tensile. So in that case, life is very simple. I simply go to the first load vector entry, and to which from which I subtract Q. This modifies the global load vector entry, the first global load vector entry, okay, and I have taken care of Q. If you remember, this is what we needed from our variational formulation. Okay. Then if I want to have a mixed type of boundary condition, that is a Robin, that is the end has a spring with spring constant k naught and an initial compression of delta naught, that is it is initially compressed by delta naught. So if it is compressed, then this part is going to apply a force of k naught delta naught in the other direction. So in minus k naught u naught. Okay. So we will take care first of this part, that is to so the total force due to this end will be in this direction k naught delta naught minus u naught. So this part is a known, this part is an unknown. Okay. So to the known part we are going to add to the load vector side, that is f glob 1 becomes f glob 1 plus k naught delta naught, because it is a compressive force, remember that. Okay. Next, what do we do? We simply, now we have to add the corresponding unknown u naught part to the stiffness side. So what do we do? Since we had the part minus k naught u naught is nothing but u1. Okay, I take it to the left hand side and I add k naught to the first diagonal term of the stiffness matrix, that takes care of the part due to the spring. Okay. So I have modified the stiffness part as well as load part in the case of a Robin boundary condition. Okay. Then I essentially end the application of boundary conditions for point 1. We have to do a similar job at the point x is equal to x NELM plus 1, that is the point XL, okay, at the other end of the domain. Okay. So this is L, this is 0. Okay. This, what does this end correspond to in terms of the degrees of freedom? This corresponds to n and offs. Okay. That is the degree of freedom or the basis function corresponding to this point is phi n and offs. Okay. So if I have to apply the boundary conditions at this end, I have to essentially modify the rows and columns corresponding to only n and offs. So again, what do we do at the end 2? If my boundary condition is the Dirichlet type, then I specify what is the known displacement that has to be applied here, that is given by the value 1. So again, I go and set the diagonal entry here. If I have this diagonal entry which corresponds to n end offs to a value 1, and I will set the last load vector entry to the value u1, okay, the specified value 1 at this end, okay. So again, what I am going to do, the rest of the column entries in the last row I am going to set to 0. So the last row is going to give me the value of the end deflection is equal to the specified value, and again what do I have to do in order to obtain symmetry? These entries have to be suitably modified, that is the global vector for all other rows, that is all the rows above, will be modified by this, sorry, not this entry, I will look at these entries, the last column. So last row and last column. So what I am going to do, f globe j is equal to f globe j minus the stiffness entry corresponding to the last column, okay. In that stiffness entry I am going to take that stiffness entry multiplied by the known displacement and value at this end, and simply subtract it from the load vector corresponding to that row, and then I will set that corresponding stiffness entry to 0. Similarly, if I have to apply the Neumann boundary condition here, for the Neumann boundary condition at this end, there is an end load P acting here, then that load has to be directly added to the last entry in the load vector, that is all. If I have a mixed condition here, so here I have a spring, I call it with stiffness K1 and an initial compression delta 1, then the global load vector gets modified by minus K1 into delta 1, and the global stiffness matrix corresponding to this last column and the last row, that is the last diagonal entry, gets modified by K1. So this is all we have to do as far as applying these boundary conditions is concerned, okay. One more thing we have to check. So in this case, for the Robin boundary condition, we have the spring end spring K1 and the end compression delta 1. So this again can be applied similar to what we had done at the end x equal to 0 by first taking the last load vector entry to which, from which we subtract this K1 into delta 1, okay, this is the part of the load, and then to the last diagonal term in the stiffness matrix we will simply add K1. You see that in this case always the stiffness entry is going to get an addition of a spring constant, okay. We cannot be subtracting. If I am subtracting, something is wrong there, okay. One more thing that we have to keep in mind is the special case when there is no distributed spring on the structure, that is, I may have this kind of a situation. There is no distributed spring and both ends have Neumann boundary conditions, okay, with or without point loads, that is not a problem. If my spring constant is 0, which I can check very easily, okay, and if the boundary condition type at both the ends is 2, which is the Neumann case, so this is called a pure Neumann problem. In this case, what happens is, if you think of this problem as I have this pen, here is a load here, we are talking of static equilibrium, then what happens? This will remain in static equilibrium, but it can have a rigid body motion, okay, a rigid body mode. This is going to reflect in our calculations. What you will see is that your stiffness matrix is going to be rank deficient by 1, okay. So there is a rank deficiency in the stiffness matrix of 1, and this corresponds to the rigid body mode. That is, I take any solution to which if I add a constant, so I get some deformation or displacement u for the various points. To these displacements, if I add a constant uniformly, then that also is a solution. Why? Because my state of strain and state of stress is not going to change if I add a constant to the displacement field. Okay? And this constant has not been constrained against. So numerically we are going to see the effect of it through this rank deficiency, and we have to now fix this constraint. That is, we have to fix this rigid body mode to a particular value. Now generally we are interested in the strains and the stresses and maybe the relative displacement of 2 points. So why can't we fix this constant to an arbitrary value? So what do? We fix essentially maybe this endpoint to a value 0. So u at 0, we fix it at 2, 0. Okay, and we find a solution. We see that this solution is not going to give you any different state of stress and strain. This is because my loads have to be in static equilibrium. Remember, one condition that has to be checked for the solution to exist, that given this load p, q and the distributed f, these p plus integral of f over the length minus q has to be equal to 0. That is, there is global equilibrium for the whole structure. If that is not true, you cannot have static equilibrium for this particular case. This thing, that p minus q plus integral of f dx from 0 to L is equal to 0, is called the consistency condition. This your load has to satisfy. Okay? If that is true, then if I fix arbitrarily the value of the first point to 0, how do I do it? I do it as if I was applying the Dirichlet condition at the point 1. That is, again I am going to set the first diagonal entry of the stiffness matrix to 1, the first load vector entry to 0, and all other entries in the first row and first column to 0. Okay? I solve the problem, I get a solution. That solution is going to be fine. Okay? Remember, this has to be done. If I have a distributed spring, say, somehow it is lying on an elastic support, then what happens? Automatically the rigid body mode is constrained against, because you cannot have a constant deflection for the bar in this case. Because why? Because if you have a constant deflection, then the spring is going to have a force, okay, and that is going to counter everything. It is going to counter the effect of the other forces if you have the constant. So in this case you can have the constant, but your stiffness matrix is not going to be singular. That one should check, that in case when k0 is not equal to 0, I have the same problem as I have done here. My stiffness matrix should not be 0, should not be singular. Okay, this is a check for your program. Okay, next part is, so we have now applied the boundary conditions also. Next part is we have to solve the problem. Okay, now how do we solve the matrix problem? Ku is equal to f. Okay, there are many options which are available to us, and one of the options, and the size of the problem is n n dots by n n dots. Okay, and we have the solve, this feature of solving the problem will be available through the routine called solver. I could call it anything. There are many options available to solve this kind of a matrix system. Remember, the system has very special properties. It is symmetric, and now it is positive definite. Okay, so it should be invertible. So one simplest possible way is the Gauss elimination, which one can see in any of the numerical analysis book. Okay, in the Gauss elimination, remember, again from the solving point of view, we have to be careful. We have to use pivoting. Okay, one should go and read up what do we mean by pivoting. Why do we need pivoting? To avoid round off errors. Here we are talking of large systems with varying sizes of the entries in the matrix, round of errors can happen. Okay, but the problem with this Gauss elimination, though it's very nice and robust, if I use fully pivoted one, is that the cost of computation is high. Okay, in fact, most of the direct solvers, which is by simply doing an elimination, do have very high cost of solution, and it is of the order of n cubed. N is the number of the size of the system, so it is n NDOPS cubed. Okay, so if you see that if n NDOPS is increasing, the size is becoming bigger and bigger, so the computational cost is going to become bigger and bigger. But here we have a banded nature, that is only in the vicinity of the diagonal the entries are going to be non-zero, elsewhere they are going to be 0. We can use that, and we essentially get n squared kind of operations. Okay, these are so-called sparse solvers. Okay, now for many such solvers are available freely. The source code of these solvers in Fortran, C, C++, and so on. One very good source for such is this website www.netlib.org. Okay, for very large systems, if you have very large systems, you see that it is available on netlib.org. We use something called iterative solvers. That is, here we don't eliminate, but we make a guess and then try to improve on this guess solution. Okay, the advantage there is that you do not have to invert the matrices, you have to simply do matrix multiplications. We are not going to talk about these iterative solvers, but these are a pretty big and important field, emerging field, especially because we want to consider more and more complex problems which need significantly large number of degrees of freedom in order to obtain a solution. Okay, what we will do in the next lecture is we are going to talk about the so-called LU decomposition based solver, sometimes called the Celluloske decomposition. Okay, and the advantage with this, it is very much similar to the Gauss elimination, but it is simply managing information in a subtle way, such that we can easily handle multiple load vectors, and once I have this kind of a decomposition of A, then we can throw away the A. Okay, and all future computations can be done with the LNU. So I am going to stop here. In the next lecture we will talk about the solver, and then we will get into the, so once the solver is there, then essentially our processor has come to an end. Okay, then we will have to now, once we obtain, so with the solver we are capable now to get a solution. Once we have the solution, to now we do what with it? Whatever comes under this doing what with the solution is in the module of the post processor. Here we will simply see how to visualize the solution, what is it that we have to do with it, and how to get better stress values out of my finite element data, etc.